Saudi Arabia is a country defined by extremes. More than 95% of its landmass is desert. Annual rainfall averages less than 100 millimeters, and summer temperatures regularly exceed 45 degrees Celsius. In many regions, rain may not fall for years at a time. Rivers are virtually non-existent, and natural freshwater reserves are extremely limited. Yet more than 37 million people live here. Modern cities rise from barren landscapes. Agriculture exists where nature never intended it to. Heavy industry, energy production, and urban life all depend on a single resource. The country lacks almost entirely fresh water. Saudi Arabia may sit atop one of the largest oil reserves on Earth, over 40 trillion liters of crude oil, but nature never gives everything. Oil can fuel economies, but it cannot hydrate a population. For every glass of drinking water, every irrigated field, and every industrial process, Saudi Arabia must manufacture what most nations receive for free. This reality forced the country to attempt something unprecedented. Saudi Arabia built a nationwide water delivery system that functions like an invisible river made of steel. Every single day, billions of liters of seawater are drawn from the Red Sea and the Arabian Gulf, processed in massive desalination complexes, and pumped hundreds, sometimes thousands, of kilometers inland through giant pipelines crossing some of the harshest terrain on Earth. Bringing water inland from the sea is already a major engineering challenge, but transforming salt water into drinkable fresh water at the scale required to sustain an entire nation is what truly sets Saudi Arabia apart. Today, Saudi Arabia is the largest producer of desalinated water in the world, accounting for roughly 20% of global desalination capacity. Cities like Riyadh, located more than 400 kilometers from the coast, rely almost entirely on desalinated seawater delivered through pipelines. This achievement did not happen overnight. Saudi Arabia's water infrastructure represents decades of investment, technological experimentation, and enormous financial cost. High-strength carbon steel pipelines, similar to those used in oil and gas transport, stretch across the desert for thousands of kilometers. Construction costs alone average around $3 million per kilometer, not including booster pumping stations or desalination plants, each of which can cost tens to hundreds of millions of dollars. But pipelines are only part of the story. The real challenge begins at the coast, where seawater contains about 3.5% salt, far too saline for drinking, irrigation, or industrial use. Removing that salt requires advanced desalination technologies, vast amounts of energy, and precise chemical control. A single large desalination plant can process millions of liters of seawater per day, consuming enormous electrical power in the process. Even after purification, the water must be chemically adjusted and remineralized before it is safe and palatable for human consumption. And all of this must operate continuously. There is no rainy season to fall back on, no river to divert in emergencies. If desalination plants stop, cities run dry. This raises an obvious question. How does Saudi Arabia build, operate, and maintain one of the most complex water systems ever created in the middle of the desert? To understand the answer, we need to start with the backbone of the system itself, the pipelines. To move water across a country where nature provides almost none, Saudi Arabia had to rely on something it already understood extremely well: pipelines. For decades, the nation had perfected the art of transporting oil and gas across vast distances. That experience became the foundation for an entirely different mission transporting water instead of fuel. The water pipeline network spans thousands of kilometers connecting coastal desalination plants to inland cities deep inside the desert. These pipelines are not lightweight conduits. They are massive industrial-scale structures built to survive constant pressure, extreme heat, shifting sands, and decades of uninterrupted operation. Most of the pipes are manufactured from high-strength carbon steel, similar to the steel used in oil and gas pipelines. This material choice is critical. The pipes must withstand continuous internal pressure from pumping stations, mechanical stress during installation, and temperature swings that can exceed 40 degrees Celsius between day and night in the desert. Each pipe begins as a rectangular steel plate cut to precise dimensions. These plates are fed into multi-axis rolling machines, where heavy rollers gradually bend the steel step by step until it forms a perfect cylinder. Typical water pipeline sections have diameters of around 8 meters with wall thicknesses approaching 25 millimeters. Once shaped, the longitudinal seam is welded using high-precision, automated welding systems. This weld is one of the most critical points in the entire structure. Any defect could compromise pressure integrity over hundreds of kilometers. After welding, the pipe is passed through a controlled water cooling line to stabilize the metal and prevent residual stress. Grinding machines then smooth all edges and corners, removing burrs and ensuring geometric accuracy. Both ends of each pipe are beveled to create optimal weld joints during field assembly. Each completed pipe section is typically 12 to 18 meters long enough to minimize the number of field welds, but short enough to remain transportable. Once finished, the pipes are coated with multi-layer corrosion-resistant materials to protect them from moisture salt residue and aggressive desert soil chemistry. From the factory, the pipes are transported to massive staging yards along the planned pipeline route. Here, logistics become just as important as engineering. Pipe sections are sorted by diameter length and installation sequence to maintain a continuous construction workflow in remote areas where delays can cost millions. Before installation begins, survey teams map the exact pipeline alignment using GPS systems and terrain data. Routes are carefully selected to avoid unstable soils areas prone to erosion and zones where shifting sand dunes could expose or deform the pipeline over time. The construction corridor itself can reach 40 meters in width, allowing multiple crews and heavy machines to operate simultaneously. Large tracked excavators dig trenches to precise depth and width, ensuring enough space for the pipe and protective bedding material. In flat desert regions, excavation is relatively straightforward, but in mountainous or rocky terrain, construction becomes far more complex. In some areas, controlled explosives are used to blast trenches directly into solid rock, allowing the pipeline to remain buried and protected even in extreme landscapes. Before any pipe is placed, a bedding layer of fine sand or screen soil is laid at the bottom of the trench. This layer distributes loads evenly and prevents stress concentrations that could weaken the steel over time. Pipe sections are then lowered into the trench using specialized side boom tractors. Multiple machines lift each pipe string in perfect coordination, keeping it suspended and aligned before slowly lowering it into place centimeter by centimeter. After alignment checks, the trench is backfilled in stages. Fine material is placed first to protect the pipe coating, followed by excavated soil compacted in layers to prevent future settlement. This process repeats day after day, advancing at an average rate of about 1.5 kilometers per day across the desert. But the pipeline itself is only a delivery mechanism. To understand where the water actually comes from, we need to return to the coastline where seawater begins its transformation into freshwater. Every drop of fresh water delivered deep into Saudi Arabia's desert begins its journey in the open sea. Along the Red Sea coastline, massive desalination complexes are positioned directly beside the water. These facilities are strategically located to minimize transport distance for raw seawater because moving untreated water inland would be both inefficient and unnecessarily expensive. The process starts offshore. Large intake pipelines are installed hundreds of meters from the coastline where seawater quality is more stable and less affected by coastal sediment pollution and temperature fluctuations. Installation crews carefully align each intake section and lower it into place using heavy lift cranes operating from barges or coastal platforms. Once assembled, the intake line is reinforced with structural frames and anchored securely to the seabed to withstand waves currents and long-term corrosion. A single intake pipe, typically around 63 centimeters in diameter, can draw in up to 15 million liters of seawater per day, more than 10,000 liters per minute. To protect marine life and equipment, the intake opening is fitted with large debris screens that block objects larger than approximately 4.5 millimeters. This prevents fish, jellyfish, crabs, and floating debris from entering the system. Even with these screens, seawater is far from clean. Once inside the plant, the water still contains suspended sand silt, organic matter, and microscopic organisms. If left untreated, these contaminants would rapidly clog membranes and damage high-pressure pumps. That's why pretreatment is one of the most critical stages of the entire desalination process. The first pretreatment step is gravity-based sand filtration. Seawater flows downward through large filtration tanks filled with layers of specially graded sand. The spaces between sand grains are small enough to trap suspended particles while allowing water to pass through. Over time, dirt accumulates on the sand surface, and the sand itself slowly moves downward against the flow of water, carrying contaminants away for removal. After this stage, the water may look clearer, but it still contains countless microscopic particles, many smaller than the width of a human hair. To remove these, the water enters coagulation and flocculation tanks. Here, large mechanical paddles stir the water while precise doses of chemicals are added. Sodium hypochlorite acts as a disinfectant, while ferric chloride serves as a coagulant. These chemicals cause tiny particles to clump together into larger masses called flocks, which then settle at the bottom of the tank under gravity. This process removes the majority of remaining suspended solids, but even that isn't enough. Before seawater can safely reach the desalination membranes, it must pass through cartridge filtration systems, the final line of defense. Inside each housing are multiple fiber cartridges with pore sizes ranging from 1 to 5 microns. As water flows through them, microscopic particles are trapped within the dense fiber structure. These cartridges are regularly inspected and replaced to ensure constant performance. Any failure at this stage could drastically reduce membrane lifespan downstream, leading to costly shutdowns. Only after passing all these stages does the water reach a state clean enough for desalination. But even now, the most difficult challenge remains. Salt is not just mixed into seawater, it is chemically bound to it. Sodium and chloride ions cling tightly to water molecules through electrostatic attraction. Breaking that bond requires immense pressure and precise engineering. That challenge leads directly to the heart of the system: reverse osmosis. Reverse osmosis is the technological heart of Saudi Arabia's water system. Salt is notoriously difficult to remove from water because dissolved ions bind tightly to water molecules through electrostatic forces. Gravity filtration and chemical treatment are powerless at this scale. To separate salt from water, engineers must apply pressure greater than natural osmotic pressure, forcing water molecules through an ultra-fine membrane while leaving salt and impurities behind. This is where energy demand skyrockets. After pre-treatment, seawater enters a series of high-pressure centrifugal pumps. These pumps are among the most powerful components in the entire plant. Pressure is increased in stages as water moves through successive compression phases, protecting equipment while maximizing efficiency. By the time the water reaches the reverse osmosis membranes, pressure typically reaches 55 to 60 bar, roughly 60 times atmospheric pressure. At this pressure, water molecules are forced through semi-permeable RO membranes with pores so small they block dissolved salts, bacteria, and most organic compounds at the molecular level. The first reverse osmosis stage removes the vast majority of salt. However, trace ions and microcontaminants remain. To meet drinking water standards, Saudi desalination plants typically use a second RO stage, operating at lower pressure but higher separation efficiency. This reduces electrical conductivity to extremely low levels, producing near-pure water. The result is water that is technically cleaner than most natural freshwater sources, but also chemically unbalanced. Desalinated water contains almost no minerals. Its pH is unstable, and without treatment, it can be corrosive to pipes and unpleasant to drink. To fix this, plants perform post-treatment and remineralization. Small amounts of calcium and magnesium are added back into the water, restoring taste, alkalinity, and chemical stability. pH is adjusted to safe levels before distribution. Only after this process is the water considered suitable for human consumption. But the achievement comes at a cost. Producing desalinated water is energy intensive. On average, modern reverse osmosis plants require 3 to 4 kilowatt hours of electricity per cubic meter of fresh water produced. In Saudi Arabia, where water demand is enormous, this translates into massive power consumption, much of it historically supplied by fossil fuels. Financially, desalination is equally demanding. The cost of producing desalinated water in Saudi Arabia is estimated at around $5 per cubic meter compared to just a few tens of cents in countries with abundant freshwater resources like the United States. Despite this, desalination is not optional. In cities like Riyadh, desalinated water accounts for the overwhelming majority of supply. Without it, modern Saudi Arabia simply could not exist in its current form. Once produced, the water enters the final stage of its journey. High-capacity pumping stations push fresh water into the national pipeline network, maintaining constant pressure over vast distances. Booster stations positioned along the route repressurize the flow, allowing water to cross deserts, climb elevation changes, and reach cities hundreds of kilometers inland. Every segment of this system must operate continuously. Any failure, whether mechanical, electrical, or chemical, risks disrupting water supply to millions of people. To increase resilience, Saudi Arabia has invested heavily in redundancy automation and monitoring systems. Sensors track pressure flow rate, temperature, and water quality in real time. Control centers can isolate pipeline sections, reroute flow, or shut down plants within minutes if anomalies are detected. In recent years, the country has also begun integrating renewable energy sources, particularly solar power, to reduce the carbon footprint of desalination. While fossil fuels still dominate, the long-term goal is to decouple water production from oil consumption. Yet even with advanced technology, enormous investment, and constant optimization, the system remains fragile. This raises a final, unavoidable question. Is this model sustainable in the long term, not just for Saudi Arabia, but for a world facing increasing water scarcity? Saudi Arabia's desalination and water pipeline system is one of the greatest infrastructure achievements of the modern era. But its sheer scale raises an uncomfortable truth: this system exists because nature failed to provide what civilization demands. As of the mid-2020s, Saudi Arabia operates dozens of large desalination plants along the Red Sea and the Arabian Gulf. Collectively, they produce billions of liters of fresh water every day, sustaining cities, agriculture, and industry in one of the driest regions on Earth. No other country relies so heavily on manufactured water. Yet this success comes with long-term challenges. The most pressing issue is energy dependence. Even with modern reverse osmosis, technology desalination remains power-hungry. Historically, much of this energy has come from oil and natural gas resources Saudi Arabia possesses in abundance, but which also contribute to carbon emissions and climate change. In response, the country has begun shifting toward more efficient systems and cleaner energy sources. Newer desalination plants increasingly integrate energy recovery devices, which capture pressure from outgoing brine and reuse it to reduce overall power consumption. These systems can lower energy use by up to 40% compared to older designs. Saudi Arabia is also exploring solar-powered desalination, leveraging its vast desert sunlight. Pilot projects combining photovoltaic energy with reverse osmosis aim to reduce reliance on fossil fuels and stabilize long-term operating costs. While still limited in scale, these initiatives signal a strategic shift toward sustainability. Another challenge lies beneath the surface brine disposal. For every liter of fresh water produced, nearly another liter of highly concentrated brine is discharged back into the sea. This brine is saltier, warmer, and often contains chemical residues from treatment processes. Improper disposal can disrupt marine ecosystems, particularly in enclosed bodies of water like the Red Sea. To mitigate this, Saudi desalination plants increasingly use diffuser systems that rapidly dilute brine before release. Environmental monitoring programs track salinity temperature and marine life impact around discharge zones. While these measures reduce harm, brine management remains one of desalination's most controversial environmental issues worldwide. Cost is another unavoidable factor. At approximately $5 per cubic meter, desalinated water is among the most expensive sources of fresh water on Earth. Saudi Arabia heavily subsidizes water prices for consumers, meaning the true cost is largely absorbed by the state. This model is viable only because of national wealth, and even then, it represents a significant long-term financial commitment. Despite these constraints, the system continues to expand. Population growth, urban development, and industrial diversification under Saudi Arabia's Vision 2030 plan are increasing water demand. New pipelines, additional desalination capacity, and smarter distribution networks are already under construction to meet future needs. Globally, Saudi Arabia's experience offers both inspiration and warning. As climate change intensifies droughts and depletes freshwater reserves, worldwide desalination is becoming increasingly attractive to coastal nations. Countries across the Middle East, North Africa, and parts of Asia are investing heavily in similar technologies. But Saudi Arabia's system demonstrates that desalination is not a simple fix. It requires enormous capital investment, technical expertise, reliable energy supply, and careful environmental management. It is a solution born of necessity, not convenience. In the end, Saudi Arabia's water network is more than a feat of engineering. It is a testament to how far modern civilization will go to survive in environments once considered uninhabitable. A nation nearly swallowed by sand now sustains itself with an invisible river of steel-pumping seawater across the desert, forcing salt and water apart at the molecular level and delivering life where none should exist. The question for the future is not whether this system works. It clearly does. The question is whether the world can afford to build many more like it, and whether we can do so without paying an even greater price.